The Hubble telescope was built to look very far into space, farther than anything we had before. For 30 years, it has been taking pictures of places that are billions and billions of kilometers away from Earth. Scientists pointed Hubble at a part of the sky that looked completely empty and dark. A piece of space the size of a grain of sand if you held it at arm's length. They let the telescope stare at this empty spot for days and days. But what appeared in the photos changed everything we knew about the universe. In that tiny speck of darkness, Hubble found more than 10,000 galaxies, each one with billions of stars. And the farther Hubble looked, the stranger things became. The most distant galaxies didn't look like anything we know. They were behaving in a way that shouldn't be possible. What did Hubble discover when it looked too far into space? Why did some of these discoveries leave scientists frightened about what really exists out there? Subscribe to the channel, leave your like and comment what part of the world you're watching from. Get comfortable and relax. Let's begin. What if I told you that looking deeper into space actually means looking further back in time, and what Hubble found out there has seriously surprised the world of science? The Hubble Space Telescope has been floating above the Earth for more than 3 decades, acting like a time machine pointed at the farthest reaches of the universe. The images it collects don't just show distant objects, they show us how the universe looked billions of years ago, right after it began. What has shocked astronomers is the discovery of ancient galaxies that simply shouldn't be there according to what we thought we knew about the cosmos. Let's talk about these weird and unexplained galaxies that have made everyone rethink how everything began. When Hubble was first launched, one of its top goals was to see as far back as possible toward the very first galaxies that formed after the Big Bang. Astronomers figured that when you look far enough, you'll reach a time in the universe's youth when everything was chaotic and primitive. Back then, galaxies should have been small, messy, and not particularly bright because there just wasn't enough time for their stars to form and organize themselves. But Hubble totally shattered those expectations. What it found out there were galaxies that didn't match those predictions at all. They looked way too mature, too organized, and even too massive, considering how young the universe should have been during those epochs. To give you a sense of the scale, when Hubble peers back at galaxies that are more than 13 billion years old, in other words, galaxies that formed only a few 100 million years after the universe started, those galaxies are already looking surprisingly evolved. Think about it. The whole universe is about 13.7 billion years old. So these galaxies formed when the universe was less than 1/10 its current age. Yet they already have clear structures, disks, and sometimes even spiral arms, which are features you'd expect to see in much older and more developed galaxies. That's not all. Some of the earliest galaxies are also much larger and more luminous than anyone suspected was possible given the timeline. The question that pops up here is simple. How did these galaxies get so big and so mature so fast? This is where things start to get weird. According to our standard understanding, after the Big Bang, the universe was a hot, dense soup of particles and energy. It took hundreds of millions of years for gravity to slowly pull together the first clumps of matter to form stars, and later, galaxies. This process was believed to be somewhat slow and steady. Tiny seeds of matter would gradually grow, merge, and form structures over cosmic time. Simulations based on these rules never predicted that you'd get large, well-organized galaxies snapping into existence almost immediately after the universe cooled down enough for atoms to form. But thanks to images from Hubble, that seems to be what actually happened. There's an example called GN-Z11. A galaxy observed by Hubble that is one of the oldest and most distant ever spotted. It exists at a redshift of about 11.1, meaning we're seeing it just a few 100 million years after the Big Bang. Instead of being some tiny faint blob, GNZ11 is a large and surprisingly bright object with lots of star formation going on. It's almost as if the timeline for assembling galaxies has to be compressed into a much shorter period than science had thought possible. Now that would be shocking enough, but similar discoveries kept happening as Hubble and other telescopes pushed ever deeper into the past. These unexpected discoveries spark a lot of questions. One of the biggest is, did the early universe have some unknown ingredients or new laws of physics that let matter and energy come together much quicker than expected? Or maybe the first stars and galaxies formed under special, totally different conditions we haven't thought of yet? For instance, it's possible that the earliest generation of stars, sometimes called population 3 stars, were unusually massive and burned out quickly, releasing huge amounts of energy and material that seeded new galaxies almost instantly. Another idea is that interactions and mergers between proto-galaxies were more violent and efficient than previously believed, helping to build up big galaxies quickly. Or perhaps there's something we still don't understand about how dark matter, the mysterious substance making up most of the matter in the universe, acted in those early times. No matter which way you look at it, the basic problem is the same. The observations don't match up with the expected timeline. If galaxies are bigger, brighter, and more mature at those early times, then our models of cosmic evolution have serious gaps. The implication is that the first billion years of the universe were a lot more dramatic and complicated than previously assumed. If these galaxies existed in such an advanced state so soon after the Big Bang, then either galaxy formation happened incredibly quickly, or some unknown process acted to speed things up. Some researchers go as far as to suggest that the very nature of time, space, or gravity might have been slightly different in those early moments. That's a pretty wild possibility, the idea that the laws of physics could change over cosmic time. What makes this whole scenario even stranger is that it's not just a handful of freak galaxies being found. Hubble's deep field and its even deeper successor, the ultra-deep field, both proved this isn't just a rare event. Both surveys involved pointing Hubble at a tiny, almost empty patch of sky and letting it soak up light for days and days. The result was a mind-blowing collection of thousands of ancient galaxies. Many of them look like they could belong to a much later period in cosmic history, not the turbulent time just after the universe's birth. This pattern has shown up over and over. The universe in its infancy just seems to be much more developed than scientific theory anticipated. These ancient, unexplained galaxies aren't just unusual in their appearance. They often contain several times more mass in stars than expected, and many have star formation rates that are way too high for the era. Normally, it would take billions of years for galaxies to gather so many stars, but these ones seem to have managed the trick in only a few 100 million years. It's as if they skipped straight past the awkward teenage years and went right to adulthood. Astronomers are now re-examining all sorts of basic assumptions like how fast gas clouds should collapse, how effectively stars can form, and whether there could be entirely new processes involved that nobody has even imagined yet. Some scientists think that there might be weird feedback effects happening. For example, when early stars formed, they might have put out such intense radiation that surrounding material collapsed even faster, creating baby booms of stars and fueling runaway growth in certain galaxies. Others have pointed out that perhaps huge reserves of cold, dense gas in the early universe made things much more efficient for galaxy building. There's still a lot of debate, and every time telescopes get sharper or look deeper, another mystery seems to pop up. The discovery of these galaxies is not just a puzzle for astronomy, it's also a reminder that we're still in the early days of understanding our own cosmic origins. The fact that galaxies could be larger, more complete, and brighter than models predicted means there could be ancient cosmic events or laws that nobody has theorized before. Some researchers are even open to the idea that the first stars might not have formed exactly the way stars do now. Maybe the first stars didn't need to go through a slow process of gathering gas. Perhaps some unknown process triggered the first wave of star formation in an explosive fashion, almost like a chain reaction across vast regions of space. One thing that helps bring this issue into focus is the way light travels. Remember, when astronomers view distant galaxies, the light has taken billions of years to get to us. So we're seeing them as they were long ago, not as they are today. If the early universe looked totally different than what we've imagined, then our entire story of how the cosmos evolved might need rewriting. Instead of a gentle, slow-growing universe, maybe it was filled with bursts of action, sudden mergers, and extreme processes that forced galaxies to grow up in a cosmic hurry. It's also worth noting that these surprising early galaxies have changed how researchers build computer models of the universe. When scientists run simulations with all the standard rules, they usually get galaxies that look much too rough or too small for those early times. The more they try to tweak the models to fit the Hubble data, the more they realize that something big might be missing from their understanding. Maybe it's a new kind of feedback process, maybe it's a different way that dark matter clumps, or it could be something else entirely. There's a growing sense that some fundamental part of the story is still waiting to be uncovered. There are also questions about what kinds of elements existed in these ancient galaxies. Normally, heavy elements like carbon, oxygen, and iron have to be cooked up inside stars and spread out through supernova explosions over a long time. But in a few cases, these ancient bright galaxies already show signs of containing these heavier elements, which suggests that earlier generations of stars had already come and gone. How could that happen so quickly? Either star formation must have started almost immediately and gone extremely rapidly, or there's some shortcut nature took that we don't yet grasp. As telescopes have improved, the Hubble findings are constantly being checked against the most up-to-date observations. Other powerful observatories, like the James Webb Space Telescope, have already started uncovering new details about these bizarre early galaxies. Some reveal clumpy and chaotic shapes, while others show surprising regularity. The better the data gets, the clearer it becomes that the first few 100 million years after the Big Bang were nothing like the calm, slow build-up that old models described. Instead, space itself may have been a far wilder arena than anyone imagined. Astronomers now talk about the cosmic dawn period with a lot more focus and urgency. The cosmic dawn is the first several 100 million years after the universe began, and it's now clear this era was both crucial and still mostly mysterious. Hubble let us glimpse it for the first time, and what we saw was full of surprises. The presence of massive, mature galaxies so soon after the Big Bang means some creative new ideas will be needed to fill in the gaps. One unusual possibility put forward by a handful of theorists is that the early universe may have contained exotic forms of matter or energy that we don't see today. Things like primordial black holes or other still hypothetical particles might have radically sped up the growth of structure in those early years. Others even float ideas about quantum effects or changes in the balance of the forces of nature back then as possible explanations for the strangeness Hubble has detected. Most astronomers stop short of these more out-there ideas, but nobody has found an entirely satisfying solution so far. The bottom line is that Hubble's discoveries about ancient, unexplained galaxies have made the first billion years of cosmic history a source of genuine mystery. Rather than fitting into neat and tidy models, the universe's beginnings look complicated, energetic, and full of unexpected developments. Instead of just answering old questions, the telescope opened up a whole new set of challenges. Now researchers are hunting for the hidden ingredients or secret rules that sped up the formation of the galaxies we see when looking to the edges of observable space. In the meantime, the pictures and data Hubble has sent back remind us that even with decades of improvement in science, the universe still manages to catch us off guard. The early universe might not have been the slow, patient laboratory for galaxy making that textbooks described. Instead, there's growing evidence that nature can do things much faster and on a much bigger scale than we ever thought possible. That's the ultimate gift and challenge of seeing so far back into time. Every new discovery has the power to change how we understand not only the past, but also the deep mechanics of the whole universe. As technology moves forward and scientists keep digging into the data, the story will get even stranger, because if Hubble taught us anything, it's that the cosmos holds secrets far outside the boundaries of even our boldest imaginations. When scientists look at the cosmos with the Hubble Space Telescope, they aren't just collecting beautiful snapshots of distant galaxies. They are also piecing together how everything fits and works on the grandest scales you can imagine. After being surprised by those mature galaxies in the early universe, researchers started to take an even closer look at what the Hubble was showing in the patterns of distant starlight, and that's when something even stranger began to emerge. It wasn't just about how galaxies were forming, it was about how the entire universe is behaving as a whole, and the clues came from the way Hubble observed distant exploding stars, supernovae, in remote galaxies. To unravel this, you have to go back just over 2 decades. At that time, scientists knew the universe was expanding thanks to earlier discoveries about galaxies moving away from us. What was unknown was whether that expansion would slow down, keep going steadily, or maybe even reverse. People thought gravity would probably tug the universe back, maybe even trigger a collapse in some far-off future. The only way to be sure was to measure extremely distant objects and see how fast they seemed to be moving away compared to those closer to us. That's where the Hubble Space Telescope became really important. Its sharpness and ability to stare deep into space allowed astronomers to spot very faint supernovae. These are massive stars that explode with a burst of light bright enough to be seen across billions of light years. Supernovae are pretty useful in a cosmic sense because they act as what astronomers like to call standard candles. This isn't a technical term. It just means these explosions always reach almost the same brightness, so if you see one and know how bright it should look up close, you can estimate how far away it really is by how faint it appears. Hubble was able to find dozens of these supernovae in galaxies that are anywhere from a few 100 million to more than 10 billion light-years away. That means seeing these explosions as they were when the universe was much younger. Here's where everything took an unexpected turn. When careful teams started examining those distance measurements, Hubble's data showed that distant supernovae were fainter than anyone had expected. If something is fainter, it's farther away, right? But these supernovae were even dimmer than the steady expansion model could explain. The only way to account for this was if, at some point, the universe's expansion had started moving faster. In other words, instead of simply coasting apart, galaxies and everything else were being pushed away from each other with increasing speed. The expansion of space itself was picking up pace. This was a huge surprise to almost every scientist watching the field. No one really expected the universe to speed up. It was the opposite of what they had been looking for. Now, when you try to figure out what could possibly make the entire cosmos push itself apart faster and faster, ordinary matter and the familiar forces don't do the trick. Gravity, for example, always pulls things together. Normal matter, even when spread thinly across the universe, tends to slow expansion, not accelerate it. This pointed scientists toward the idea that some completely different ingredient was at work, something they started calling dark energy. The word dark here just means it's mysterious and invisible. It doesn't give off light, can't be detected with telescopes in any normal way, but it exerts an influence everywhere. It's not the same as dark matter, which acts through gravity. Dark energy is a different concept. It acts as a sort of anti-gravity, causing everything to move away from everything else more rapidly over time. Hubble's role was key because its deep surveys provided the rock-solid distance and brightness data that people could trust. The accelerated expansion theory basically rose from those careful measurements. No single observation, no one document could have settled the issue, but Hubble's supernova studies, backed by other ground and space-based telescopes, built a mountain of convincing evidence. And this is where the idea starts to settle in, that the universe is a far stranger place than anyone had predicted, because now we had to accept that most of it is made up of something we can't see or feel, yet it shapes everything. The numbers that come from these measurements are staggering. Scientists estimate that about 70% of the universe's total content is dark energy. That leaves about 25% or so as dark matter, stuff that only interacts through gravity and not light, and a mere 5% as the regular matter that makes up stars, planets, and people. This means nearly all of reality is invisible and strange. Hubble didn't just help introduce the existence of dark energy. Its follow-up observations refined how much of it there is, how consistent it seems to be through time and space, and how fast it's making the universe expand right now. An interesting fact is that Hubble's legacy images, those famous deep fields full of thousands of galaxies, aren't just pretty pictures. They are statistical goldmines for measuring changes over time. By studying galaxies at different distances, essentially seeing them at different ages, scientists can spot how quickly the universe was growing at various stages. Supernovae observed at many points in cosmic history allow teams to build timelines, measuring not only how far, but at what rate expansion happened billions of years ago compared to how fast it's happening now. What consistently pops up in those results is evidence for this accelerating push, a steady, silent force pulling space apart, a major discovery that scientists credit in large part to Hubble. People sometimes wonder, how do you even picture this acceleration? There's no edge to the universe, no spot where it's expanding into something else. What's happening is that every bit of space is getting stretched, and this stretch happens more and more strongly through time. Galaxies aren't flying through space in the way a car drives down a road. Instead, they're mostly sitting in place, and the space between them is increasing. Hubble's ability to see galaxies from every era lets scientists actually watch this process play out across billions of years. The further away an object is, the faster it appears to be retreating from us, and by measuring that effect with the help of standard candles like those supernovae, the change in pace becomes apparent. This expansion isn't just a curiosity, it leads to serious questions about the future and fate of everything. If the universe keeps expanding faster, galaxies that are currently visible will, after a few tens of billions of years, drift beyond the limit that even light can cross to reach us. The night sky would become emptier. Advanced civilizations far in the future might only observe isolated stars and galaxies in their neighborhood. Hubble didn't just catch this trend in the act, it gave us the numbers to run calculations about where it all may be headed. Scientists have been modelling several hypothetical endings for the universe based on what Hubble and other telescopes are showing now. If dark energy remains constant, the universe will continue expanding at an ever-quickening rate, eventually resulting in what's called the Big Freeze, or heat death, when all matter is too spread out to interact and temperatures drop close to absolute zero. Alternatively, if dark energy somehow becomes stronger, there's a scenario called the Big Rip. Space itself could expand so violently that even atoms are torn apart, long after every galaxy has vanished from view. On the other hand, if dark energy were to reverse or fade away, which there is no sign of yet, some speculate about a possible slowdown or collapse, but current Hubble evidence all points the other direction. All of these possibilities hinge on dark energy's bizarre properties, and here's something wild. Scientists, using Hubble data, have tried to see if dark energy's effect has changed over time. So far, every measurement lines up with the idea that dark energy acts almost like a constant pressure throughout all of space, and has done so for nearly all of cosmic history. This fits the simplest version of the so-called cosmological constant, an idea that dates back to Albert Einstein, who, in the early 20th century, introduced it in his equations to fudge a static universe, then abandoned it when expansion was discovered. Now, it turns out, some form of his cosmological constant, or at least something that behaves a lot like it, seems to be behind the scenes after all. Being able to see so far in space and time with Hubble has also forced people to search for dark energy, using every method possible. Astronomers look for its signs in the way clusters of galaxies grow, in the tiny wiggles of the cosmic microwave background, and in how great walls and voids arrange themselves on the largest scales. Yet the primary, clearest evidence comes down to those supernova distances and the rates at which they recede, something Hubble excels at collecting. What keeps this an open and fascinating field, though, is that nobody knows what dark energy really is. The data tells us what it does, but not what it is made of. It doesn't seem to be energy in the traditional sense, like that of moving objects, heat, or electricity. It is also uniformly spread, so there's no way to point to a spot and say, there's more dark energy here than over there. It doesn't clump or form structures. Its defining trait is to push space apart and do it everywhere equally. The numbers the Hubble has helped produce show that this force, or effect or property, whatever it turns out to be, is by far the dominant component of the universe, utterly overwhelming all the matter and energy tied up in galaxies, dust, stars, black holes, or anything else. Because of the reliability of Hubble's observations, other scientific teams across the world have tried to double and triple check these results with brand new telescopes from the ground and space. Every time a fresh measurement comes in, it confirms what Hubble showed. The universe's expansion isn't slowing down, it's speeding up, and nothing so far has shaken that fact. That intense agreement is actually a rare thing in science. Physicists and astronomers are both frustrated by how little they can say about the cause and impressed with how certain they can be about the effect. It's a weird situation and one that makes cosmic science genuinely exciting. Digging deeper, astronomers have asked if there might be early dark energy, a variant that acted even more powerfully at the start of the universe and then faded. Others have looked at whether dark energy could be tied to undiscovered particles, fields, or hidden properties of space itself. Hubble doesn't see these causes directly, but the telescope locks down the consequences across billions of light years. The fact that it's so hard to explain only increases interest, especially as new surveys keep turning up more evidence to support Hubble's original findings. This story affects how scientists look at almost everything in the universe. Galaxies were once closer together. Now, because of accelerating expansion, their light is stretched and faded as it travels to us. When Hubble takes those crisp, sharp images at various distances, it isn't just giving a view across space, it's giving a window across time. Charts made from Hubble's measurements provide the backbone for almost all modern models of cosmic growth and change, and any new theory has to match what Hubble reveals about the acceleration rate. There's another side effect as well. The discovery of dark energy has made scientists more cautious about claiming to know the full inventory of everything out there. When the most dominant factor in running the cosmos is basically a mystery, it adds a layer of humility to the picture. Yet there's still continuous progress. Hubble keeps monitoring supernovae, and every so often, new observations give hints that might someday serve as clues about the true nature of dark energy, whether it might slightly change with time or be related to any new physics. So far, the evidence is consistent, but nobody can rule out unknown surprises as future generations build on what Hubble started. In practical terms, what Hubble showed is that the universe is expanding faster and faster, and this is due to some kind of invisible energy filling all of space. This isn't science fiction, it's a direct result of careful measurements, patient surveys, and a lot of checking and rechecking by teams worldwide. If the universe is going to continue racing apart, then the future will look very different from the present. More emptiness, less ability for galaxies to interact, and a cold, isolated fate many billions of years from now. The whole history and destiny of the cosmos have to be rewritten around this discovery. And yet, despite everything we know about how widespread dark energy is, nobody understands where it actually comes from or how it fits with the rest of physics. There are tons of ideas: fields, quantum effects, connections to the vacuum of space, and more. But Hubble's role has been to point at the effect, pin down the measurements, and make the puzzle clearer and sharper for others to try to solve. The telescope showed that there's an enormous gap between what we can observe and what we can explain, and that's a sign of just how rich and mysterious the universe remains. What's fascinating is how basic questions, how fast is the universe expanding, does that change, and what causes it, can turn up such profound answers when the right technology is put to the test. Hubble's images and brightness data forced scientists to rethink what's possible on the larger scales, and in doing so, exposed gaps and mysteries that today's researchers are still struggling to fill. Using its unmatched view and stable orbit above Earth, Hubble has been able to give back data that's both incredibly consistent and deeply strange. As the telescope continues to look into space, astronomers keep applying new techniques to its observations. Sometimes they find small twists that create even more questions, such as whether dark energy acts precisely the same everywhere, or if there might be small variations on the very longest scales. The search is ongoing, and every new bit of information helps sharpen the bigger picture. So, from all these deep surveys and the detailed monitoring of exploding stars across billions of light years, we're left with a universe that isn't just bigger and older than we guessed. It's also governed by a force that's so mysterious. Most of what we see is just the beginning of the story. Every measurement Hubble delivers pushes the limits of what we know and forces scientists to keep hunting for answers about what dark energy is and where it comes from. In the process, the entire view of cosmic evolution is forever changed, pointing to a universe where most of its story remains hidden, waiting to be decoded. And as researchers explored these deep mysteries like the true nature of dark energy, they also stumbled on something that didn't fit neatly with any straightforward explanation about how the universe works. Through years of careful Hubble observations, scientists began to notice a strange, large-scale motion taking place across huge regions of space. Instead of only focusing on the way galaxies are moving apart because of overall cosmic expansion, teams started looking at how entire clusters of galaxies drift with respect to the universe itself. This led to the discovery of a phenomenon now known as dark flow, one of the weirdest and most unsettling patterns in modern astronomy. You might expect, with everything we know about the expansion of the universe, that galaxies would just move apart from each other in a uniform way. The basic idea is that space itself stretches, making galaxies recede from each other pretty evenly on average, no matter where you look. This smooth, large-scale movement is the basis of what's called the cosmological principle. In simple terms, it means the universe should look the same everywhere if you zoom out far enough, and nothing in one giant region should behave very differently from any other part. For decades, this principle seemed to work really well, and it matches what most computer models show when simulating billions of galaxies. However, as data from Hubble reached greater distances, astronomers decided to analyze how giant clusters, a cluster being a group of hundreds or thousands of galaxies bound together by gravity, were drifting compared to the gentle flow of expansion expected from dark energy and the regular pull of gravity. They targeted some of the most massive clusters they could find, looking at galaxies stretching out over hundreds of millions, even billions of light years. What they uncovered caused a lot of head-scratching. Areas of the cosmos, sometimes spanning hundreds of millions of light years, seemed to be drifting in the same odd direction, as if being pulled by something far beyond what's visible in the observable universe. The way they spotted this odd motion was through a clever trick involving the cosmic microwave background, the leftover light from the very early universe. That ancient light acts like a backdrop to everything else in the sky. When a massive cluster moves, it can slightly alter the temperature of the cosmic background light that passes through it, a subtle shift called the kinematic Sunyaev-Zeldovich effect. Using this, astronomers tracked how whole galaxy clusters seemed to show a steady movement toward a particular patch of sky. Over and over, data showed that these clusters weren't just spreading out evenly due to expansion, they were all drifting in one broad direction and at considerable speed, hundreds of kilometers per second. This became known as the dark flow. Here's where Hubble's sharp vision, combined with data from surveys like WMAP and Planck, made a huge difference. Hubble provided the detailed images, precise distances, and maps of galaxy clusters at different epochs. This allowed astronomers to confirm that dark flow was not just a local oddity. It's not about some nearby cluster acting up. It's something affecting immense volumes of space, well outside what local matter could explain. These flows cross vast swathes of the observable universe and just keep going, defying easy explanation by any normal gravitational attraction from known objects. What's especially odd is that none of the structures or galaxies we can see within the boundary of the observable universe are nearly massive enough to pull galaxy clusters in this way. Ordinary matter, and even the combined gravity of both dark matter and visible stuff, shouldn't make such a large-scale movement possible. This makes dark flow stand out. It seems, based on the direction and consistency of the movement, that whatever is causing this flow is coming from well beyond the farthest galaxy we can detect. Some astronomers straightforwardly admit that it could be caused by a concentration of mass outside our observable universe, a region we simply cannot ever see because light from there hasn't reached us yet. Others suggest it's a hint of physics that's not in our standard models. What's even more intriguing is that the evidence for dark flow did not come from a single look with Hubble, but through the careful piling up of results across many years, comparing one cluster, one patch of sky, and one epoch after another. This approach, repeated with Hubble's long-term stability and precise imagery, gave weight to the idea that the phenomenon is real rather than a mistake in measurement or a result of some local small-scale effect. So what are the possible explanations for a phenomenon like dark flow? One possibility involves the idea that soon after the Big Bang, right as our observable universe was separating from the rest, some incredibly massive objects outside our cosmic horizon caused a gravitational pull on everything in our region. That pull started galaxies drifting in a certain direction in the earliest moments, and since nothing has interfered since, they just keep moving the same way. These objects could be vast clumps of matter, maybe other giant cosmic structures, or something even stranger that's simply completely beyond the reach of our telescopes. Maybe regions with much greater density, or possibly remnants of a much older universe. Another possible explanation that some experts have proposed is that dark flow could be evidence our universe is larger and stranger than we think, possibly even just a small piece inside a much bigger, more complex multiverse. If some neighbouring universe or region outside our own has wildly different properties or much more matter, its gravitational impact could reach over to affect us, at least on the grandest scales. While that idea takes us into a realm of speculation, the raw data suggesting that something is tugging on enormous clusters in a preferred direction can't be ignored. Scientists remain cautious, and there is still plenty of lively debate about whether the effect is real or is caused by some as yet unknown systematic error. Not every researcher fully agrees about the significance or even the reality of dark flow. There are always checks and rechecks happening as more data is gathered. Other telescopes and cosmic surveys help confirm or question the trend. Some analyses suggest the effect is less strong than first indicated, while others keep finding evidence it's out there. But the original hint and continued investigation owe much to the ability of Hubble to survey large stretches of space with consistent, high-quality data. Scientists use these checks as a way to refine the measurements because small errors can look like big patterns over cosmic distances. If dark flow is confirmed in the future, it is is a direct challenge to the idea that our universe is the same everywhere on the biggest scales. It's precisely this cosmological principle that sits at the center of most modern astronomical models. The discovery of a preferred direction, a kind of cosmic current, changes how everything from the birth of structure to the distribution of galaxies is considered. That would force major revisions to simulation models and our basic understanding of how the universe behaves across distances too great to ever see fully. There's also the unsettling possibility that if this movement is being caused by something outside the visible universe, we may never get a good look at what's behind it. Unlike problems where you can simply build a bigger or better telescope, here, the source of the effect would be physically out of reach forever thanks to the limits set by the age and size of the universe and the speed of light. So, if dark flow is pointing to some supermassive structure or event beyond our cosmic horizon, its nature might always remain a mystery. Scientists can measure its consequences inside our universe, but might never be able to explain exactly what's behind it. Looking at dark flow as it stands today, scientists are doing what they can. They're carefully charting the motion of clusters using every new generation of images and distance measurements from Hubble and other modern observatories. They use improvements in computer simulations to ask whether some more subtle explanation, some early fluctuation or effect from physics just after the Big Bang, might be able to account for the observation. They also try accounting for all known biases in measurement to make sure nothing on Earth or in our methods is creating a false signal. There's also the question of whether dark flow could tie into even more exotic theories, like higher dimensions of space. Some versions of string theory allow for extra dimensions that we do not experience directly, but that could influence gravity or the behavior of matter on giant scales. Although these ideas are far from proven, the mere existence of puzzles like dark flow gives theorists room to explore options they otherwise would not consider. Every time data from Hubble or similar telescopes captures galaxies drifting together with the same off-axis speed, it offers new hints to these types of explanations. The reality of science is that sometimes big discoveries come from noticing what doesn't fit as much as what does. The ability to track galaxy clusters across huge distances with confidence was only possible thanks to the steady, crystal-clear images Hubble provided for decades. These images allowed astronomers to map not just where galaxies are, but how fast they're moving through the universe, and in what direction. That's a level of overview that's hard to get without dedicated, long-running space missions. Meanwhile, the effort to pin down the nature of dark flow continues with new instruments and fresh looks at the microwave background data. The results so far remain fascinating, drawing attention and raising questions every time someone finds another cluster moving the wrong way. If future surveys keep finding the same patterns, dark flow will stand as a powerful reminder that not everything in the universe follows the patterns we expect. Looking at the broader picture, dark flow gets added to a growing list of cosmic puzzles that Hubble and its fellow space telescopes have uncovered. It shows how discoveries about the universe are often a mix of what we set out to find and what turns up on the fringes, sometimes in the data we almost overlooked. With every pass through another region of the sky, telescopes like Hubble can catch tiny clues, slight temperature shifts or unexpected group motions that change the questions scientists are asking about all of reality. As these mysteries accumulate, they become part of the foundation for new investigations, pushing researchers to double-check what's possible on cosmic scales. Hubble's contribution to the dark flow discussion isn't just in the discovery, but in laying out clear, repeatable measurements future scientists will use to settle the matter. If dark flow proves to be real and remains unexplained by familiar physics, it could shift the focus of research toward answering questions about what lies outside the part of the cosmos we can observe, and whether our universe really is a typical patch of reality or something even stranger. So, the idea of dark flow doesn't only concern the motion of galaxies, it reaches into the heart of cosmology, touching on how we define the universe and what hidden forces or regions might shape what we see. When combined with all the other mysteries uncovered so far, unusual galaxies, cosmic acceleration, the invisible push of dark energy, it's one more sign that the story told by Hubble's images is not nearly finished, and that every answer brings up new, bigger questions. While dark flow brings up big questions about the largest forces acting on our universe, there's another layer of strangeness that Hubble has helped uncover, one that makes you realize how much of reality is actually invisible to us. With its sharp eyes, Hubble has given us astronomers the ability to peer not only at the objects that give off light, but at the spaces in between, uncovering signs of something massive hiding in plain sight. This happens thanks to a strange effect called gravitational lensing, and it keeps showing us that the cosmos is shaped mostly by things we cannot see. Gravitational lensing isn't a new prediction. It was first worked out by Albert Einstein back in the early 20th century as part of the whole idea that gravity curves space. It means that when a huge mass, like a cluster of galaxies or even an individual galaxy, sits between us and something bright and far away like a quasar or another galaxy, the light from that background object doesn't travel to us in a straight line. Instead, it gets bent around the massive thing, kind of like light bending through a lens. The result is that we might see weird, stretched arcs, rings, or even multiple images of the same source appearing around the lensing object. Hubble, with its cosmic view uncontaminated by Earth's atmosphere, can catch these delicate distortions in detail, bringing out shapes that ground-based telescopes would easily miss. It turns out that these lensed images are not just odd photographic effects, they are direct evidence for the presence and amount of mass in the universe, no matter if that mass is visible as stars, gas, or if it's totally dark and invisible. The bending is only about the mass involved, not what that mass is made out of. That's where things get interesting, especially when Hubble's deep fields and surveys started picking out lensing effects that don't match up with what can be seen directly. Over and over, astronomers have come across situations where the amount of bending is much greater than what you'd expect if you only counted up the visible matter, meaning there's extra mass, but we can't see it. Scientists call this unseen component dark matter, and it shows up not just in lensing, but also in how galaxies rotate and how clusters behave. Yet with gravitational lensing, Hubble lets us map where this dark matter is and how much of it there might be, galaxy by galaxy and cluster by cluster. Astronomers can use the patterns and distortions in the images to actually reconstruct an invisible, sometimes called a mass map, which tells them the locations and concentrations of dark matter even when there are clearly not enough stars or gas there to explain the effect. This has fundamentally changed how people think about structure in the universe. Instead of being made mostly out of the stuff that shines or glows, all the largest things in the cosmos, galaxies, groups, giant filaments, are stitched together mostly by something that's completely dark. One thing that stands out is that dark matter has turned out to be extremely widespread. According to the best measurements from Hubble and other support from lensing studies, about 85% of all matter is this invisible component. When you zoom in on a giant galaxy cluster and measure how light from more distant galaxies is twisted and spread around it, in pretty much every case, the bulk of the mass producing the bending isn't made of visible stars or nebulas or even black holes. Most of it is a dark halo, or sometimes an even larger structure surrounding the visible stuff. Sometimes the visible part is just a tiny drop at the center of an enormous unseen mass region. Hubble's resolution has been vital in making these detailed maps and in catching the smallest lensing features that reveal how distributed or clumpy the dark matter really is. Hubble has helped spot some of the biggest gravitational lenses ever found, like galaxy clusters that act as sort of cosmic magnifying glasses for things far behind them. There's a famous example called Able 2216, which sits more than 2 billion light-years away and bends the light from even more remote galaxies behind it. This produces intricate wisps, arcs and smears, bright streaks that Hubble's camera can pick apart in a way that shows scientists just where and how much mass is sitting in the cluster. Some of these lensed galaxies are among the most distant ever seen, magnified many times by the cluster's enormous hidden mass. What surprises researchers is just how much of the lensing is extra, beyond what any telescope can find by simply adding up the stars, gas and dust. In individual galaxies too, Hubble's close-up look at lensing events tells a story of small but powerful masses that aren't luminous at all. Sometimes entire bands or regions of a galaxy appear to have clumps of hidden mass that cause background light to split or smear, even though there's nothing obvious visible in those spots. In some cases, these distortions only make sense if there are clouds or pools of dark matter billions or trillions of times the mass of the Sun lurking nearby. Astronomers working with Hubble data have even been able to use gravitational lensing to weigh galaxies and clusters. The calculations go like this. More bending of light means more mass, regardless of whether that mass is bright or dark. Time and again, the measured lensing says there must be a lot more mass out there than what we can see. And sometimes lensing even reveals dark objects that aren't associated with any galaxy at all. These could be dark matter lumps or subhalos left over from the very early universe, structures that only show up because of their effect on passing starlight. Not only does this change our picture of the cosmos, it also points to a limitation in our senses. Hubble, in a way, lets us measure the shadow cast by things that have no light, broadening the meaning of what's really out there. The telescope has provided much of the clearest visual proof that the visible universe is just a small part of the story, with dark matter shaping the paths of galaxies, the behavior of clusters, and even the growth of cosmic filaments over billions of years. With every new high-resolution image, some new lensing arc or faint distorted feature might point to another concentration of mass we can't otherwise detect. Some galaxy clusters catalogued by Hubble contain so much unseen mass that the background objects are bent into perfect or near-perfect rings, called Einstein rings. These striking features offer a direct window into the amount and distribution of mass, and are so sensitive that by carefully measuring the arcs, astronomers sometimes even detect small, individual clumps of dark matter floating alone, with no visible galaxies tied to them. These isolated, dark structures would never be found, except for their effect on the light behind them. The study of gravitational lensing has even let researchers watch how dark matter acts over time. In clusters that have collided or merged, like the famous bullet cluster, Hubble images have shown that the visible matter and the dark matter can actually get separated from each other, moving through collisions in different ways. In these situations, lensing maps made from Hubble photos show the overall mass sticking in places where there's very little visible light, while the glowing gas and stars slow down or pile up somewhere else. This offers a direct sign that dark matter isn't just ordinary stuff that's dim, but a fundamentally different kind of matter, one that doesn't interact with normal material except through gravity. Despite all these advances, the nature of dark matter is still a mystery. Hubble's role isn't so much to discover exactly what dark matter is, but to guide where new particle physics experiments should look by showing where and how much of it exists. There are lots of ideas, from entirely new types of particles that don't react to light, to more exotic possibilities, but gravitational lensing tells scientists where the invisible stuff has its biggest effects. Sometimes researchers also find small lensing incidents, called microlensing, where a single star or compact object acts as a lens, briefly magnifying a more distant star. These let astronomers hunt for certain forms of dark or hidden mass in otherwise empty parts of galaxies. Thanks to decades of Hubble data, astronomers are now building up a detailed map of the dark universe, a framework that's crucial for understanding how galaxies formed, how they grow, and why large-scale structure looks the way it does, without dark matter. Most galaxies, including our own, would not rotate the way we observe or hold together over time. Actually seeing the effects directly, as in the lensing images Hubble captures, turns what could be dismissed as a mathematical trick into a visual, concrete fact. It's also worth noting that not all gravitational lensing is obvious to the naked eye. There are subtle statistical effects, called weak lensing, which don't produce giant arcs, but just slightly change the shapes of thousands or millions of galaxies across a huge patch of sky. Hubble's ability to look at deep surveys, imaging large numbers of galaxies with a single shot, helps astronomers pull out these tiny distortions and build up huge mass maps that cover more of the universe than ever before. These studies keep confirming that dark matter is everywhere and is the key player almost everywhere structure is found. The presence of all this hidden mass hasn't just changed how scientists explain the universe today, it's also changing how researchers think about the ultimate fate of the cosmos. Since dark matter makes up the backbone of galaxies and clusters, how it behaves, does it ever decay? Does it interact with itself in unexpected ways? Could influence what happens on cosmic timescales. And since gravitational lensing images can track the movement and distribution of mass over time, keeping an eye on how structures shift may one day offer hints about dark matter's true identity. Every time a new survey stacks up more cases of unexplained lensing, another piece is added to this map of the unseen. The mass that holds the universe together is just not made out of the same stuff that builds stars and planets. As untidy as this may sound, Hubble's lensing discoveries show over and over that what's most real in our universe is most hidden from our eyes. This pushes scientists to be both more skeptical of assumptions based purely on visible light and more creative about new ways to look for for invisible influences. Recently, teams working with Hubble and newer telescopes are going even further. They're trying to use strong and weak lensing combined with other observations, such as X-rays from galaxy clusters or radio maps, to get the best picture so far of the dark web, the large-scale skeleton of dark matter that connects galaxies with cosmic threads. These efforts are producing the sharpest, most detailed mass maps ever built, revealing hidden bridges between galaxy clusters and tracing the outlines of structures hundreds of millions of light-years wide, totally unseen except for their effect on faraway starlight. All these results keep reinforcing the idea that the majority of the universe's mass is neither near us nor made from familiar atoms. The images Hubble collects are kind of like a treasure map, except most of the treasure is locked in invisible vaults we can only find by looking at what they do, not by what they are. Even so, every new gravitational lens adds another place for physicists to look for answers. Whether it's for new types of particles, powers of gravity, or another piece of cosmic structure we've never considered before. So, as scientists dig through Hubble's massive archive and keep scanning the skies for new lensing events, they're slowly building a much more complete and honest model of what's out there. This view tells us not just about the stuff we can see, but about the powerful, massive structures that hide in the dark and shape the fate of galaxies, clusters, and maybe the future of the universe itself. It's a discovery that continues to grow more important every year, showing just how much science can reveal when we take seriously that most of reality is out of sight, but never out of mind, and seeing how most of the universe's mass is hidden away in these dark halos, revealed to us only through gravitational lensing, makes you look at the big picture in a new light. With Hubble's unmatched detail, astronomers haven't just pieced together where unseen mass is, they've also been able to map the universe's structure at some of its largest and smallest scales. But along the way, as Hubble peered even deeper through those dark clouds, it began picking up evidence that the blueprint of the early universe wasn't what most textbooks would have predicted. The structures Hubble found out there, especially at very large distances and faint signals, started to look more bizarre the closer you looked. Instead of just the slow, steady build-up of small galaxies merging into bigger ones over billions of years, Hubble's snapshots pull out cosmic features that seem much more dramatic and frankly surprising. There are places where everything is relatively empty for huge distances. These are called cosmic voids, and right next to them are lines of galaxies traced out like threads, known as filaments, stretching hundreds of millions of light years. These filaments can connect into bigger structures called walls, creating a kind of web pattern that wasn't expected to be so well defined just a few billion years after the universe began. Digging into Hubble's images even more, scientists started to realize that in some regions, the density of galaxies is shockingly high, far above what most models predict. It's like entire clusters of matter managed to clump together in a cosmic blink, much sooner than they should have been able to, according to simulations. In other places, galaxies seem scattered almost randomly, surrounded by emptiness so deep that it almost breaks with the idea of a universe evolving smoothly and predictably over time. Whether you look at a snapshot from more than 10 billion years ago or closer to home, there's this pattern of cosmic irregularity, surprises in both the concentration and the emptiness. What confuses many researchers is that the standard theory for how the universe evolved after the Big Bang describes a process filled with order and predictability. Small ripples in the early universe, caused by quantum fluctuations and stretched out during inflation, were thought to act as the seeds for galaxies. Gravity was supposed to pull matter together slowly over time, smoothing things out and building up regular shapes. But Hubble keeps finding giant voids bigger than you'd expect even after factoring in randomness, or finds dense, busy zones that look much more advanced than simulations typically produce for those early times. There's also the issue of galactic shapes and arrangements. Hubble's best images of far-off galaxies show some with clear spirals and disks, forms that take time to develop. According to most evolutionary models, those elegant features shouldn't be so common so soon after the universe came to life. Some galaxies at huge distances appear so tidy, with tightly packed stars in regular orbits, that researchers have had to rethink how fast that kind of order could emerge. In other frames, though, Hubble picks up chaotic structures, galaxies interacting, crashing, stretching each other out, or tangled so violently together that it's impossible to say where one ends and another begins. These chaotic, unpredictable structures have forced astronomers to question the completeness of classic models. For example, many assumed that cosmic webs, these intricate networks of voids, filaments, and walls, would take a long time to come into their current forms. But Hubble, peering into the deep past, finds versions of these large-scale patterns appearing far too early. One of the biggest surprises is just how sharply defined some boundaries are. In some cases, galaxies at the edges of voids seem to track along the dividing line almost perfectly, creating sheets and threads that hold together despite spanning hundreds of millions of light years. Such highly organized skeletons across that scale were supposed to be rare or even impossible in the early universe. It's also worth mentioning the nature of the voids themselves. When Hubble zooms in or takes a deep look, it sometimes finds emptiness more profound than anyone expected. These are not just areas with fewer galaxies than average. They're vast regions with almost nothing, sometimes stretching across spaces so large that even the faintest galaxies barely appear. In other directions, there are signs of superclusters, gigantic groupings of galaxies bound by gravity and spread across distances larger than anything you can find locally. These cosmic contrasts, huge empty voids right next to dense knots of galaxies, challenge the idea that the early universe was a gentle blend of stuff swelling outward. Some researchers looking at this evidence wonder if we might be seeing hints of unknown forces or new types of physics at work during the first billion years. Maybe gravity worked slightly differently under the extreme conditions back then, or perhaps dark matter had properties that let it gather in these ways faster than expected. Others suggest that small initial differences in matter density could have had huge effects, growing rapidly rather than slowly. As Hubble and other telescopes gather more data, the questions grow sharper. Why these outsized knots and gaps? What started the filaments and walls so early? And do these structures tell us about something that happened in the first seconds after the Big Bang? On top of that, Hubble has found some of the earliest cosmic collisions, where galaxies or even entire clusters smash together and trigger rapid, chaotic changes. These events seem to have been more common and much earlier than many scientists thought. Instead of the slow, stately merging of galaxies over time, it looks like the early universe featured a storm of activity, with galaxies and clusters slamming into each other and sending shockwaves of new star formation across space. Some images show lines of bright new stars strung out in the aftermath, while others reveal galaxies flung apart as violent forces reshape them. Galaxies formed in this chaos display strange properties. Some are highly asymmetric, looking more like lopsided blobs than anything with a central core. Others have tails, bridges, or plumes trailing off as material is pulled away during interactions. These features, all captured in detail by Hubble's imaging, hint at a universe where disorder and violence, not just calm and gradual order, played a major part in shaping what we see now. Comparing these forms to modern simulations shows that our ability to model cosmic evolution still isn't complete. Something is missing in how we think the earliest stars and galaxies came together. Another layer of weirdness comes from the chemical content of some of these structures. Hubble is able to split apart the faint light of distant galaxies and measure what elements are present. Sometimes it finds heavier elements, like oxygen, carbon, or magnesium, already present in galaxies that formed only a few 100 million years after the Big Bang. According to older models, there shouldn't have been nearly enough time for stars to cook up and spread those elements so quickly. Their presence suggests bursts of star formation and violent supernovae were happening at breakneck speed very early on, further skewing the picture away from slow, steady growth. It's not just the galaxies themselves. Hubble's wide-field surveys have mapped out large sheets and filaments of gas, sometimes stretching across millions of light-years, that trace the cosmic web. These structures, invisible in regular light but detectable through their subtle glow or effects on more distant objects, are another dimension of irregularity. They act as a kind of scaffolding, supporting galaxy formation along their lengths and speeding up how quickly galaxies can condense in some regions versus others. The presence of these gas filaments even helps explain why regions of the universe look so different, why one area might be full of galaxies while another is almost empty. Here is another twist. In some cases, Hubble's views suggest that supermassive black holes, which live at the centers of most large galaxies, were able to form and grow enormous much earlier than models had anticipated. Their gravitational pull could drive the formation of dense, bright regions and set off jets and bursts that inject energy into the cosmic environment. This would help create the irregular shapes and power the chaotic structures that show up so vividly in the telescope's images. It turns out that rather than only being a byproduct of slow galaxy growth, these black holes might have played a central role in shaping how galaxies and cosmic webs evolved from the start. With all these findings, one thing has become clear. The early universe was not a calm, orderly place slowly taking shape along well-laid plans. If anything, it was a stage for wild processes, sudden concentrations, and bursts of activity that made structures emerge much faster. And stranger than most scientists would have dared imagine, this has forced a change in how researchers build their computer models of the cosmos. Many simulations now include more chaotic feedback effects, like powerful outflows from supernova or black holes, or even the impact of early dark matter movements in an effort to match the tangled and dense universe Hubble actually sees. Hubble's long timeline also means that astronomers can directly compare structures at different cosmic ages. That's helped expose another oddity. The overall pattern of voids, filaments, and sheets seems to have been set surprisingly early and then stayed mostly the same, just growing in scale as everything expanded. This implies that something about the basic rules of structure formation in the universe sets these patterns deep in the past, and then the rest of the universe essentially fills in the details. It's as if most of the cosmic scaffolding was already in place, just waiting for normal matter and galaxies to move into position. On a smaller scale, the Hubble Space Telescope has seen examples of so-called extreme objects that offer further clues about the universe's irregular upbringing. For instance, some dwarf galaxies contain older populations of stars than predicted, or host supermassive black holes when they shouldn't really have the mass to support them. Others appear in odd places, like isolated groups far outside regular filaments, or with shapes that simply don't fit what simulations show for galaxies at their age or size. All these outliers pile up, challenging scientists to come up with models that account for more randomness, more rapid growth, and a wider range of possible histories. Researchers have even used Hubble images to look for repeating patterns, trying to understand if the universe's wild structure is truly the same everywhere, or if some regions stand out. Sometimes they find weird alignments, like strings of galaxies all spinning the same way, or clusters arranged at odd angles to the main filaments. These anomalies don't crop up in every survey, but when they do, they fuel debate about the early universe's true initial conditions and whether there's something we're still missing in the very first physical laws. One of the most important things that comes from all of this is how crucial small biases and new discoveries can be. For example, as new generations of instruments like the James Webb Space Telescope join Hubble, they confirm that what Hubble found wasn't a fluke. They spot yet more dense zones, unexpected voids, and chaotic clusters, often extending even further back into the universe's infancy. This kind of cross-checking shows that the irregular and surprising structures in the universe are not just a feature of our instruments or the way we look at the sky, but are real, physical aspects of the way the cosmos assembled itself. As observations pile up, the big picture emerging is that cosmic history is not a gentle, predictable story. Instead, it's a tale filled with rapid changes, wild differences in density, and huge contrasts between emptiness and clustering. The Hubble Space Telescope has played a central role in building this new understanding. Its deep field images provide snapshots of the universe at different ages, laying out a timeline full of surprises that force us to reimagine what it was like on the largest scales. The huge voids, the tight knots of galaxies, the early webs and walls, and even the chaotic smaller objects. These are not glitches or mistakes, but clues to a universe much more dynamic and sometimes more violent than ever expected. So, when you look at any one of those famous images, giant arcs of galaxies, faint smears billions of light years away, tangled clusters with strange shapes and empty spaces next to packed filaments, it's worth thinking about all the unseen complexity behind that view. Every shape and arrangement, every odd cluster or lonely galaxy tells a story about how the earliest ingredients of the cosmos moved and grew and sometimes crashed together. The evidence Hubble collects pushes scientists every year to rebuild their models so they line up better with reality instead of with neat, outdated predictions. All of this means cosmology is still a field in constant motion, where every new look at distant parts of the universe might add another twist. What we once took as simple, orderly progress now looks more like a collection of clashing patterns, fast changes, and strange exceptions. And through all of this, Hubble continues to deliver the snapshots that show not just the beauty of space, but its unpredictability, right back to the dawn of time. The disorder and variety of structures in the early universe, as shown through Hubble's powerful images, have made researchers look closer at what's out there, not just in the familiar forms of galaxies and clusters, but in the signals, the actual marks and traces that drift across space. After years spent building incredible, detailed maps of the cosmos, Hubble has acted almost like a listening post for odd phenomena that can't easily be filed under just stars and gas. This careful, sustained watch has led scientists to check and recheck any signals that don't line up with the known behavior of cosmic objects. Some of what's been picked up has astronomers scratching their heads, and more than once the idea's come up. Could it be that at least a few of these signals come from something beyond basic physics, maybe even the actions or artifacts of extragalactic civilizations? One place where this starts is with Hubble's unmatched ability to record very faint, distant changes in light over time. Its stability and the lack of atmospheric interference mean that very small fluctuations, things that might go unnoticed from the ground, are reliably measured in orbit. These changes, often charted as light curves, are like timelines of brightness from far-off stars, galaxies, or even things that are too far to resolve as more than a point of light. Some light curves behave exactly as expected, matching what's known about exploding stars, accreting black holes, or dust clouds passing by. But Hubble's archives also contain light curves and energy bursts that behave in unusual or unexplained ways, outliers that fall outside of normal categories. In several well-documented instances, Hubble has observed signals, some as repeating, brief brightening, and others as strange dips that defy immediate clear classification. Instead of the regular flicker of a binary star or the slow fade-out of a distant supernova, these phenomena sometimes suggest sharp, engineered patterns, uniform pulses, abrupt pauses, or energy blips in bands that don't match what's expected from known objects. Some show patterns that seem too regular or too complex to be due only to known astrophysical processes. At the same time, these are rare, surrounded by thousands of noise events or natural variations, so every marginally odd signal gets looked at again and again by teams of researchers who use Hubble data and then cross-check with ground-based follow-up. A well-known type of unexplained signal involves what are sometimes called transient events. These are bright blips, flares, or pulses, sometimes lasting minutes or even less, that just don't match the known classes of cosmic outbursts. Hubble's ability to monitor distant galaxies over weeks or months means it catches things no other telescope can see. Some of these transients turn out, after analysis, to be rare examples of stellar activity, but a handful stay unexplained. The classic scientific approach is to exhaust every possible natural source before raising the possibility of something else, like technology or intelligence. But the mere fact that these strange flickers keep appearing hints that the universe may hold surprises completely unrelated to stars and gas. Then there's the matter of energy signatures, sort of like a coloured fingerprint for each event, collected as Hubble breaks down incoming light into its component wavelengths. Most naturally occurring signals show very smooth curves, with certain drops or spikes at the places you'd expect from elements like hydrogen, helium, or iron. Some of the odd events, though, come back with jagged, sharply defined breaks or spikes at places not predicted by normal physics. Sometimes these show up as repeating shapes over hours or days, as if someone or something is switching a signal on and off in ways that are hard to explain as simply random or natural. These are the signals that get a lot of attention, even when scientists can't say with certainty what's causing them. Astronomers who notice these outliers are extremely cautious. The first step is to rule out errors in the detectors, confusion with cosmic rays, or some accidental processing glitch. But after that, the hands-on work begins. Does the sudden dip or rise in energy match what's seen from a rotating neutron star, the throw-off of material from a dying star, or a momentary lensing event? In most cases, a new or rare natural explanation eventually emerges, but never for all of them. Occasionally, the signals have no ready match, and the responsible teams flag these as unclassified events, passing them on to broader research networks for fresh eyes and new theories. Alongside these light curve and spectral oddities, there's another kind of signal that's been scrutinized: sudden radio or infrared pulses. While Hubble isn't primarily a radio telescope, it often works in tandem with ones that are sharing sky coordinates and timing to see if a cosmic event seen in light is also firing off energy in other bands. Sometimes a strange rise in optical brightness matches a sudden radio burst with a regular pulse or an energy jump out of line with what a dying star or black hole would be expected to emit. These coincidences draw even more focus because they suggest well-timed, possibly coordinated activity across huge stretches of the electromagnetic spectrum, not something you'd expect from random cosmic chaos alone. Now, zooming out for context, most astronomers will tell you that 99% of strange cosmic signals turn out to have natural explanations: new types of variable stars, interactions in dense parts of galaxies, odd angles that make one-off events look stranger than they are. After careful study, most odd signals are absorbed into an expanded list of what the universe can do on its own. But there's always that last 1%, events that stubbornly evade classification, even after multiple teams dig into the raw data and check known catalogues. These are what keep the search going and what make people return to Hubble's archives year after year. One of the hottest questions is whether any such signal could point to technologies or intelligent life vastly more advanced than us, what people sometimes call technosignatures. These would be deliberate or accidental broadcasts, mega constructions that block or alter light, or energy use so great that it changes the normal look of a star or galaxy. Hubble has been used to look for some of these hypothetical markers, such as sudden, repeated dimming in a remote star that might suggest a giant structure passing in front of it. Or astronomers scan for repeating, very narrow-band signals, impossibly precise, as if made by technology, not nature. There are also searches for weird, persistent objects like Dyson spheres, which are giant artificial shells around a star that might trap much of its light. If something even vaguely like that existed elsewhere in the universe, its fingerprints, a sharp drop at some wavelengths, an excess at others, might be visible to a sensitive and stable instrument like Hubble. No proven examples have ever been found, but the search continues with every new deep mosaic Hubble produces, because even a single confirmed anomaly, after being ruled out as natural, would be such a profound discovery that it would reshape everything about humanity's relationship to the cosmos. Some teams use the Hubble Space Telescope's databases to search for laser flashes, bursts of light at a single narrow frequency, which nobody thinks could be produced by simple chemical reactions or any one star's normal activity. A laser flashed across thousands or millions of light years would need a fantastically advanced sender, but it would stand out above the messy background of ordinary starlight. Still, despite some interesting candidates over the decades, no repeatable, verifiable laser-like beacons have shown up so far. It could be that they're just rare, or aimed somewhere else, or use methods and wavelengths our current instruments can't even spot. There's also the category of energy waste or heat. Civilizations using immense amounts of energy, as some theories suggest, might give off a noticeable amount of infrared light, basically waste heat from their activity. Hubble's more limited in the infrared than newer telescopes, but combined searches across multiple observatories let scientists set upper limits on just how much artificial heat could be out there, and so far even the best candidates have always been explained by natural, if extreme, cosmic sources like supermassive black holes or starburst galaxies. It's important to highlight how careful astronomers are not to jump to conclusions. Just because something is strange doesn't mean it's alien technology. The process goes like this. Scrutinize every signal, pass it through panels of skeptical researchers, and try to reproduce the finding with other telescopes or by examining other bands of light. Only after every ordinary explanation is exhausted does anyone even begin to talk about non-natural possibilities. This caution is partly because of past lessons. Many promising alien signals, from radio bursts to wobbles in stars, have been overturned by new data or explained by rare natural events. But even with all that skepticism, Hubble's dataset has become a kind of reference for this search. Its archive of faint, steady images lets astronomers return again and again to check on past outliers, see if patterns repeat, and compare the behavior of thousands or even millions of cosmic objects. The discovery of anything that doesn't fit, especially if it happens more than once, could open doors to further targeted studies from other specialized observatories. Some dedicated researchers are now developing machine learning tools to sift through the mountain of Hubble archival images and spectra, hoping to spot repeating patterns or rare configurations that might slip past a human observer. The universe is so vast, though, that even multiple decades of Hubble observations only offer a tiny window. There are billions of galaxies and even more stars, each with its own history and chance to produce weird light or radio signals. Add in that Earth's own technology, satellites, communication beacons, sensors, and even lightning can produce phantom signals that fool the most well-designed searches, and you see why the hunt for true techno-signatures remains slow, detailed, and filled with false alarms. Still, this search for subtle signals, whether repeating pulses, sharp interruptions in starlight, or excesses in odd wavelengths, expands every year. New generations of telescopes, launched with deeper sensitivity and wider reach, use Hubble's findings as their baseline, checking back and forth to see if the faint hints spotted in one place show up elsewhere. Sometimes patterns found in other galaxies mirror what's seen locally. At other times, completely unclassified surges or dips spark a wave of new proposals, from superluminous supernovae to naturally occurring lasers to, yes, the hopes for real alien activity. Hubble's contribution, then, isn't just in making discoveries, it's in setting the gold standard for what unknown looks like in deep space. By gathering light curves, spectra, and deep mosaics in a consistent, reliable way, it's given scientists a huge set of templates. This is what a known black hole looks like. Here's the signature of a mature, stable galaxy. There's how a typical nova or gamma-ray burst behaves. Any new signal can be compared instantly, sharpening the boundary between what fits and what doesn't. This makes the rare, persistent outliers easier to notice and much more important to probe. While nothing that quite fits the classic idea of a broadcast from another civilization has turned up in Hubble data, the effort itself keeps pushing the science forward. Every odd light curve or unexplained pulse is a chance to learn something new about cosmic dust, about rare supernova types, about the hidden activity in distant galaxies. The process keeps expanding human understanding of what's possible in space, and every bit of data is another clue in the ongoing search for meaning in all those millions of faint signals reaching us from the deep night sky. The search also drives new technology and methods. Better software, improved algorithms for pattern detection, and closer partnerships between ground and space-based observatories now mean that almost any rare or suspicious event can be checked quickly by multiple teams in several types of light. And as archival Hubble data keeps growing in depth and coverage, it becomes possible to spot trends that just couldn't have been discovered in a single night, or even a single year of observation. Big data, as it's sometimes called, is the new normal for cosmic signal hunters. With all the disciplines moving in parallel, astronomy, physics, computer science, even engineering, each promising or stubbornly unclassified signal becomes a jumping-off point for debate and investigation. The most likely outcome for now is that most strange signals are phenomena the universe itself produced naturally, rare but possible given the wild diversity of space. But the mere hunt for artificial or distant intelligence forces scientists to keep an open mind, to dig deeper, and to check every assumption. That's why, today, Hubble's observations act both as a catalogue of cosmic phenomena and as a kind of open notebook, always being revisited and updated as tools and ideas advance. Even when natural explanations win out, the journey never feels wasted. That process teaches more about the complexity and unpredictability of distant space than any single easy answer could. Each faint, strange flicker in Hubble's record of deep space is a reminder that for all humanity's breakthroughs, the universe still regularly throws out questions we're not quite ready for. And every generation of astronomers working through years of archival data finds a few more cosmic mysteries, some that go into the books with an explanation, but others that remain open, waiting for new eyes, new tools, or maybe even a message that finally reveals we're not alone. Even as astronomers dig through Hubble's deep archive looking for unexplained signals that might, just maybe, hint at distant intelligences, the telescope's imagery is also packed with evidence of the universe's own brand of extreme activity. If you spend any time at all studying Hubble's records, one thing stands out again and again. The universe is not a gentle, peaceful place. In fact, it's full of violence and upheaval that's nearly impossible to grasp until you actually see it in these crystal-clear snapshots collected over more than 3 decades. What makes this so compelling is that Hubble, with its high-resolution imaging, has caught the aftermath of some of the universe's most powerful collisions. These collisions are happening on scales that dwarf anything on Earth. Hubble's sensitive cameras have documented the wakes of enormous events, 2 entire galaxies smashing together, colossal black holes joining forces, and the glowing remains of gigantic stars detonating as supernovae. Each of these events tells its own story, yet all point to an underlying reality. Cosmic structures are built on a cycle of destruction and creation. When Hubble points at galaxy clusters, some of the most dramatic images it returns are those of merging or colliding galaxies. A classic example is the antennae galaxies, a pair of spiral galaxies that have been caught in the process of merging. In these images, you can see huge tidal tails of stars and gas where the 2 systems are being stretched and torn apart by tidal gravitational forces. Long streams of material are pulled from the main bodies, arcing away sometimes for hundreds of thousands of light years. These bridges are not just decorative. They're regions rich in star formation, set off because the collisions compress massive clouds of interstellar gas, setting off chain reactions that cause thousands of new stars to ignite. But it gets even wilder. Hubble has followed dozens of cases where entire clusters of galaxies, each containing billions of stars, can be seen interacting or passing through one another. During these collisions, the clouds of hot gas that surround each cluster slam together and heat up to enormous temperatures, emitting strong X-rays that Hubble and other space observatories can detect. These collisions are so energetic that they can alter the structure of whole clusters, tearing them apart or fusing them into even larger structures. Over millions or billions of years, this is how some of the universe's biggest formations, the superclusters and walls of galaxies, have come together. These cosmic smash-ups are not just rare or isolated events either. Every major galaxy, including our own Milky Way, has signs of past encounters, and more are happening all the time. Hubble has shown us bridges of stars left as evidence of old collisions, dwarf galaxies being absorbed into bigger ones, and often surprisingly regular-looking galaxies hiding chaotic collision scars when you look closely. In our own cosmic backyard, scientists know the Milky Way is on course to collide with the Andromeda Galaxy in a few billion years, a slow-motion crash that will reshape both galaxies completely. Then there are the black holes, sitting at the heart of most large galaxies. When 2 galaxies merge, there's a high chance that their central black holes will eventually spiral toward one another and collide. These mergers are powerful enough to send waves through the fabric of space itself, called gravitational waves. While Hubble doesn't detect gravitational waves directly, it can see the after effects, the jets of material blasted away from galactic centers, energetic flares, and changes in brightness when black holes consume huge amounts of matter at once. In some of Hubble's deepest images, you see the signatures of these mergers, active galactic nuclei shining with a blue-white light, or the twisted, off-center shapes of galaxies still settling after a cosmic encounter. Hubble has given us an almost cinematic look at the life cycle of stars as well. Among its most iconic images are those of dying stars blowing themselves apart in supernovae. When a star many times more massive than our Sun reaches the end of its life, the core collapses and the star blasts its outer layers into space. Hubble has watched these fireworks in distant galaxies, tracking how the shockwaves travel outward and trigger the formation of new stars in their wake. Sometimes these supernovae are so bright that for a short while they can outshine the entire galaxy in which they've exploded. These powerhouse explosions aren't just fireworks for show, they create and hurl outward elements like carbon, oxygen, and iron, which eventually become planets and even the building blocks of life. Hubble has spotted supernova remnants, the billowing clouds left behind, stretching for light years in all directions. Some still glow with faint light for centuries, slowly cooling as they mix into the interstellar medium. By analyzing the light from these remnants, Hubble helps astronomers figure out exactly what's produced in these powerful events. On top of all that, Hubble can resolve the details of phenomena like gamma-ray bursts, which are brief but mind-blowingly powerful explosions thought to come from the collapse of extremely massive stars or mergers of neutron stars. These bursts can last from less than a second to several minutes, but the energy released in that moment can be greater greater than what our sun will emit over its whole lifetime. In the moments and days after these bursts, Hubble zeroes in to catch the fading afterglow, often finding it sits in the weirdest or most chaotic zones in remote galaxies. Gamma-ray bursts are important because they could potentially affect the chemistry of galaxies or even sterilize any developing planets in their path. Of course, all this violence leaves scars. Hubble's long-term monitoring has shown us galaxies in all stages of aftermath. Some are broken apart with odd shapes and distorted spiral arms. Some have huge gaps where stars have been ripped away. Others show tightly wound cores surrounded by endless debris. One thing that stands out is how all this destruction is closely tied to creation. New stars are born in the compressed knots of gas left behind by collisions or supernovae. Many galaxies with wild, irregular shapes are in fact starburst galaxies, busily forging stars at a pace dozens of times faster than others of their size. Researchers have also discovered that major collisions can trigger the growth and feeding of giant black holes. When material falls into these monsters, it forms a disk and heats up, shining so brightly that it can outshine all the stars in the galaxy. These active galactic nuclei are a source of X-rays, ultraviolet, and sometimes even radio emission. Hubble's ultraviolet and visible images are used to track how these blazing cores change over days and years. By comparing streams of images over time, astronomers get to see how much these massive energy engines fluctuate and how their jets can stretch out thousands of light years. Evidence for violence goes all the way back to the early universe. Hubble has captured light from galaxies as they looked billions of years ago and found that chaotic, ongoing collisions were the norm, not the exception. In some of the deepest images, you can actually measure the rate at which galaxies merged, and it turns out this was happening more frequently than it does today. That's probably because matter was much closer together then, with everything packed into a smaller volume. These early collisions helped shape the familiar patterns of the cosmos, from the largest clusters to the intricacies of smaller galaxies. All these violent events have big side effects. For example, the collision of galaxies or galaxy clusters can strip material away, forming faint tidal streams that, over time, serve as the raw material for new stars, or sometimes trigger the formation of smaller satellite galaxies. Black hole outbursts, meanwhile, can blow huge holes in galaxies, clearing out vast regions of gas and putting a hard stop to star formation for millions of years. These feedback loops are now a well-studied process in galaxy evolution, and Hubble's observations offer direct proof of how energy released by collisions sculpts and sometimes limits the growth or shape of a galaxy. Even at smaller scales, Hubble has helped capture the effects of stellar collisions and the chaos in young star clusters. Newborn stars are often packed tight in clouds that can contain thousands of others just like them. Eventually, some are pushed together by gravity or by the movement of surrounding material, and the collision process can kick off powerful outflows, jets, and bursts of radiation that are visible with space telescopes. Some images show baby stars wrapped in swirling disks of gas, while others appear locked in pairs or groups, bound together from violent beginnings. If you trace the history of a single galaxy through Hubble's lens, you see a repeating cycle. Collisions with neighbors, new stars igniting by the thousands, older generations of stars exploding or blowing away bubbles of gas, clouds of debris spiraling in toward the center, and black holes feasting on the leftovers. Each stage feeds the next. This constant mixing, pulling, and destruction is what drives galaxies to their present forms, fills interstellar space with the ingredients for planets and life, and sparks a constant churn of energy at every tier. The idea of cosmic violence is maybe most clear when you consider the sheer power on display. A single galactic collision releases more energy than every star in that galaxy will make in its life. A supernova's shockwave can travel for thousands of years before it finally slows down. The largest black hole jets sculpt galaxy clusters, blowing out shapes that are visible for hundreds of millions of years. Hubble has provided not just snapshots, but time-lapse views, tracking how these features change season after season, sometimes even mapping the movement of individual gas clouds over several years. Sometimes the violence can have lasting, unpredictable results. There are galaxies left warped, stretched, or separated by earlier collisions. Even our own neighborhood bears traces. A handful of globular clusters orbiting the Milky Way are thought to be the remains of galaxies long ago devoured. Much of the faint, unseen material surrounding large galaxies may be leftovers from these interactions, and every so often, Hubble images a stellar stream, the ghostly trail of a past galactic meal. Even though this might sound chaotic, it's not all random. Hubble's deep field studies have made it clear that violence is a fundamental part of the cycle that shapes everything about galaxies. Without these crashes, there wouldn't be the bursts of star formation, the mixing of gas and dust, or the eventual recycling of material to make the next generation of stars and planetary systems. All these discoveries point to the fact that our universe's beauty comes hand in hand with ferocious power. Each time Hubble captures a new supernova flash or watches as two galaxies begin to merge, it's observing the same process that's been underway since the very dawn of cosmic history. These snapshots and time-lapse views in Hubble's archives remind us that behind every peaceful, star-filled night sky is a record of events so powerful that they change the fates of entire galaxies. The more closely astronomers have looked with Hubble, the more the story of the universe has become not just one of expansion, but of ongoing, relentless activity and transformation, where enormous losses and unimaginable creation are two sides of the same cosmic coin. All of that ongoing violence and transformation captured in Hubble's images doesn't just reveal how galaxies and stars are made and remade, it also gives astronomers a way to look back across time itself. One of the wildest facts about looking at deep space is that you're really looking into the distant past. The farther away an object is, the older the light you're seeing. That simple truth lies at the core of much of what Hubble does, and it brings up another set of weird effects that scientists have to wrestle with every time they push their instruments to the cosmic edge. What happens when you're not just looking at faraway places, but trying to measure events that actually took place billions of years ago? This is where the idea of time dilation and the challenge of the observable universe really stand out. Whenever Hubble snaps a photo of something extremely far away, say a galaxy that's 10 billion or even more than 13 billion light-years out, it's almost like getting a postcard that was sent before Earth even existed as we know it. That light had to travel through all the expanding space in between. It's not just a straight shot either. Space itself has been stretching for that entire trip. Because of this, astronomers have to deal with the effects first predicted by Albert Einstein's theory of relativity. The two big things that come up are the stretching of light, called redshift, and the stretching of time, called time dilation. The easiest way to picture this is to think about a supernova, a star blowing up in some galaxy on the far side of the universe. If Hubble watches that explosion, scientists know what kind of light pattern, the light curve, they should expect from this kind of star based on thousands of closer examples. But for the ones really far away, Hubble sees everything stretched out, including time. If the explosion would last 30 days for a close event, the same type of event billions of light years away will appear to last longer, maybe 60 days or even more, because the universe has expanded so much since that light started its journey. That extra slowing down is relativity in action, and Hubble has measured it again and again. This time dilation is more than just a curiosity, it's a real effect that astronomers have to correct for any time they're working out the history of stars, supernovae, or even the life cycles of whole galaxies. It's built right into how the universe works, and every distant event is showing us not only what happened, but how the fabric of space and time has shifted since then. In practice, this means a lot of mathematical back and forth. Teams studying a super-distant galaxy have to take apart the image, adjust for the redshift, recalculate the timescales, and sometimes even reinterpret what they see, because the familiar rules are stretched in strange ways. But things get even trickier the farther you go. Past a certain distance, galaxies aren't just moving away because of their velocity through space. Space itself is expanding, and it's doing so at a changing rate. This adds another twist. Some of what's visible in the very deepest Hubble images doesn't even exist in the same way today, simply because those galaxies have moved far enough that, with the cosmic expansion, any new light leaving them now will never reach us. That boundary is known as the cosmic light horizon, and it defines what is meant by the observable universe. Every year, as time passes, that observable bubble grows, but light from outside that bubble just hasn't had enough time to reach us since the universe began. What's really striking is how the stretching of time and space starts to mess with how astronomers interpret data. If you see a distant galaxy and want to compare it to something nearby, you have to realize that you aren't just looking at a younger version of the same type of thing. The actual processes, behaviours, and even the amount of time it takes for stars to be born, live, and die might look off-kilter because you're watching them through the lens of these relativistic effects. When Hubble observes a supernova going off at a billion light-years distance, the whole event appears slowed down, drawn out, and its light stretched far into the red, sometimes even out of the visible range and into the infrared. For the most extreme cases, this redshifting is so dramatic that the objects can only be seen by highly sensitive detectors working at wavelengths far beyond what human eyes can pick up. One of the most interesting consequences of all this is that the deeper astronomers look, the more they're peering into a strange landscape where time and space behave differently. It's part of why working out the precise history of the universe is so tricky. Hubble's observations get fed into simulations and models that have to account for not only gravity and the movement of galaxies, but also the speed at which the fabric of reality itself is stretching. Scientists have to ask, what would this look like if we could see it without the effects of cosmic time dilation? When models get it right, they can use observed distant supernovae or galaxy spectra to nail down the rate of expansion, the so-called Hubble constant. But there's always uncertainty, and every new find seems to push that calculation just a bit further or demand a minor correction. Another weird effect from all this is the way the universe's history gets stacked into shells of observation. Hubble's deep fields, these famous mosaics built up over many hours or days, let astronomers separate objects by distance and by extension by age. Light from a galaxy in the foreground may be only a few 100 million years old, while something behind it might be showing us a slice of the universe from more than 10 billion years before now. It's like peeling onions, with each layer carved out by how long the light has travelled. Sometimes features that look like they should be connected, a faint beam or glow, turn out to be wildly separated in time, the light from each reaching us now purely by chance. Time dilation and expansion also affect what events can be observed at all. There is only so much information that reaches us within the lifetime of the universe, and the faster expansion gets, the harder it is to catch glimpses of the real beginning. For example, some gamma-ray bursts so far away are so stretched and faint that only their afterglow can be measured, making identification much harder. Some of the most ancient galaxies registered by Hubble appear extremely red, almost invisible in regular light, because every step of their history is filtered through the cosmic growth of space. All the clocks are running on different speeds the deeper you look, and every analysis becomes a kind of race to untangle what's cosmic time effect and what's true astrophysical behavior. There are cases where the stretching of time and the limits of the observable universe even create conflicts in measurements. Some distant galaxies or exploding stars appear unusually slow or dim because the expansion has taken their energy and stretched it to the breaking point. Scientists sometimes debate whether these odd-looking events are genuinely strange astrophysics at work or simply a trick of stretching time and expanding space. Hubble's consistent imagery has become a key reference point for teasing apart these questions, helping astronomers create better corrections and more accurate models that account for the universe's shifting framework. If you go just a bit deeper, all these effects start to blur some of the sharp boundaries between past and present. Because of time dilation, astronomers can see very early galaxies frozen in the act of forming, explosions unfolding at an excruciatingly slow pace, and light from cosmic events blending together across eons. For the most distant supernova or nascent galaxies, what Hubble records can seem almost like a movie slowed to one frame every 100 years. It is both a gift, letting scientists rewind the cosmic tape, and a challenge, because it makes it so difficult to build one-to-one comparisons across time. Another important aspect is how this relativistic stretching and expansion limit the scientific detail that can be extracted from the oldest light. Even the sharpest telescope can only do so much when the information is diluted by over 13 billion years of cosmic change. For many of the faintest objects, only fragments of their story survive: an overall colour, a single distinctive flash, or a faint chemical signature. Every attempt to reconstruct what the early universe was like involves layers of uncertainty, where the difference between a real observation and an effect caused by light's long journey is never fully clear. A further challenge comes from the way expanding space changes the scale of everything across time. The distant galaxies Hubble photographs aren't just small because they're far away. Their physical size in the universe's youth may have been different thanks to the compressed, denser state of the cosmos back then. That means scientists always have to be sure that when they're comparing images, structures, or star clusters from different epochs, they're making fair assessments. It's easy to misjudge whether you're seeing an inherently tiny object or a big one seen under the squeeze of early universe conditions. By continually pushing up against these challenges, astronomers have developed new strategies for measurement and observation. Sometimes they use standard candles, like particular types of supernova whose brightness and timing are well known, giving a scale for corrections. Other times, they look for spectral patterns in the light from galaxies that stay consistent over time, allowing redshift to be precisely calculated. Hubble's data is crucial in both workarounds, acting as both the test case and measuring stick for how cosmologists balance raw observation with the tricks of stretching space and time. With all of these hurdles, there's always a degree of caution. Any claim about the first galaxy or the oldest supernova comes with layers of caveats about time dilation, cosmic stretch, and limits of observation. Telescopes newer than Hubble, such as the James Webb, are trying to further close those gaps. But for now, the Hubble Space Telescope remains the gold standard for observations that reveal how space and time have interacted for over 13 billion years. These effects are not just academic. They shape how researchers talk about everything from star formation rates to the evolution of galaxies. For example, when an early galaxy looks like it's forming stars at an incredible pace, that observation must be untangled from the cosmic clock that's running differently at that epoch. Otherwise, what seems extraordinary might just be the natural result of looking so far back in time. Even the basic concepts of before and after become tricky at these distances. Time becomes stretchy, and the past gets layered in ways that make every slice of sky a collection of ages. Sometimes, Hubble images show what looks like a bustling, dense grouping of galaxies, only for analysis to reveal that they're not all in the same place at the same now. Their light just happens to reach Earth together. Piecing that together is a big part of the work astronomers do as they transform Hubble's pictures into an actual story of cosmic evolution. So next time you see one of those famous Hubble deep fields, hundreds or thousands of tiny galaxies glowing against a velvet background, just remember, you're actually seeing the echoes of hundreds of millions to billions of years of cosmic history. The closer you look, the more you're watching time slow down, stretch out, and pull apart everything on the grandest scale imaginable. Hubble's sharp images are not only photographic, they're time machines that force us to face all the strange side effects of living in a universe that's been expanding since the very beginning. Every distant point of light is another chance to learn how reality itself changes when you try to see all the way to the edge. Looking at how Hubble lets us peer across time and see everything stretching, slowing, and behaving in ways that feel almost unnatural at the limits of the observable universe, it's not surprising that astronomers have started noticing things that don't fit the usual cosmic script. One of the most head-turning developments from all the deep and detailed images Hubble has taken is that, despite decades of refining our models, there are still some patterns, features, and oddities that plain old physics struggles to explain. These clues aren't just fun cosmic trivia. They've made scientists wonder if our universe is the only one out there, or if it's actually part of something much, much bigger. This is where the idea of the multiverse comes in, and Hubble's findings have been at the center of that discussion, pushing the boundaries of what anyone thought telescopes could even hint at. Astronomers using Hubble and other tools have always expected to find minor irregularities when mapping the oldest light in the universe, which is called the cosmic microwave background. It's basically the afterglow of the Big Bang and covers the whole sky. But as they started looking more closely and with better instruments, Hubble included, there were some spots that really stood out. One of these is the so-called cold spot, an area where the background light is noticeably cooler than everywhere else. At first, this kind of odd region might seem like a measurement error or a fluke, but years of rechecks, cross-checks, and studies with various telescopes keep bringing us back to it. A cold spot like this is a weird thing because if the universe formed and expanded just as our best standard theories predict, there shouldn't be any really big isolated patches that look this out of place. It would be like finding a single huge freeze mark on an otherwise perfectly baked cake. The leading explanations have included everything from random statistical noise to the effects of huge voids in space, those spots in the cosmic web where there's just not much matter at all. Hubble's high-resolution work lets astronomers check what's in the neighborhood of these cold spots, which means mapping out galaxies, gas, and dark matter to see if anything locally can explain the drop in temperature. Sometimes no clear answers come up. The voids do seem to exist, but even the deepest ones don't seem big enough to account for the whole size, sharpness, and persistence of these patches. As the cold spots, and a few other subtle oddities and alignments in the cosmic background, keep resisting easy explanations, cosmic detectives have gotten more creative. The discussion turns to whether there might have been something totally unexpected affecting our patch of the universe billions of years ago. One far-out but genuinely considered idea is that our universe actually bumped into another universe at some point in its early history. The theory is that if multiple universes or bubbles form in a larger expanding reality, which some versions of cosmic inflation predict, it's possible that these bubble universes might collide or push up against one another. When that happens, it could leave a smoother or colder patch in the otherwise pretty even background. It's possible, and some researchers are keen to point out the word possible, that what we're seeing in the cosmic microwave background are actual fingerprints or scars left behind from that kind of early collision. Other Hubble observations line up with these oddities. Over the years, astronomers have found certain alignments and patterns in galaxy surveys that don't fully fit what would be predicted if everything were totally random and driven by only one set of physical laws. Some clusters of galaxies appear larger or more tightly grouped than statistical chance would predict, especially at very great distances. Sometimes, odd lines or walls of galaxies show up where you'd think the distribution should be smoother. Occasionally, specific regions show repeated orientations or properties that make people ask whether they're seeing the natural result of one universe's chaos, or the faint echo of something even stranger happening beyond our accessible reality. It's not just temperature or position either. There are hints in the way some galaxies move, spin, or even seem to lose or gain energy that could point to faint gravitational nudges. Some cosmologists have speculated that if another universe came close enough to ours, its gravity might very slightly tug at vast regions of clusters or cause minute shifts in their growth or luminosity. While no one has a direct, simple physics test for this yet, the anomalies persist and keep being debated because Hubble's data lets astronomers weed out a lot of simpler mistakes or random errors. Added to this is the fact that many versions of modern inflationary theory, the math that explains why the universe is so big, flat, and uniform in the first place, naturally predict way more than just one universe. If inflation happened in bursts, it could produce many bubbles, each one a universe, all with their own versions of physics and matter. Ours just happens to be one with the mix needed for stars, planets, and life like we know it. In this scenario, some kind of scar, cold spot, or unexpected arrangement in our visible universe could be the fossil evidence of a time when another bubble universe got a little too close, or even overlapped with us, before inflation settled everything down. Hubble's bird's-eye view stretches so far across time and space that it really is our best tool for finding such echoes, if they exist. There's also been talk about possible axis of evil alignments in the cosmic microwave background. Large-scale patterns that seem oddly lined up, as if some outside influence imprinted its own direction or order on our universe long ago. Some of the largest galactic structures Hubble has mapped occasionally line up in ways that seem statistically improbable, given the rest of what's observed. While most of these oddities seem subtle, the more data gets collected, the less they look like pure artifacts of error or limited vision. Instead, they invite more elaborate models, sometimes invoking unknown early universe physics, sometimes suggesting two or more universes brushing past or partly merging somewhere near our cosmic horizon. If you're mapping out the edge of the observable universe, you're actually up against a barrier. No light or information can travel faster than space's own expansion, so anything out there beyond our cosmic horizon won't ever be visible to us. Its signals are locked away forever by the mathematics of relativity. Still, if something did cross over or interact with our universe in its very first moments, the aftermath could be faint but still inside our observable patch. In that sense, Hubble's depth and sharpness are like an archaeological survey, looking for cracks, lines, or colors in the layers of old cosmic light that might betray hidden structures. Research teams all over the world pull together Hubble's measurements with data from telescopes like Planck or WMAP. They analyze the cosmic background for matching anomalies, cold spots, hot spots, ring patterns, statistical outliers. The hunt for these clues is a real part of modern cosmology. It's not just theoretical fun. Proving or disproving alternate universes would totally change how humanity thinks about its own place in the cosmos. Yet, everyone agrees, extraordinary claims need extraordinary evidence. So far, the Hubble findings have built a case for real anomalies, but nobody claims absolute proof. Instead, they publish, critique, and repeat, looking for more, sharper ways to distinguish between the random fluctuations that any chaotic cosmos can produce and true signatures of universes beyond our own. Alongside these temperature and structure anomalies, some researchers dig into the statistical properties of how early galaxies are distributed across space. They simulate universe after universe, shuffling the rules and initial randomness, trying to match what Hubble actually observes. Every time an unusual match comes up, for example, huge voids in places that shouldn't have them, or unexpected alignments, they add another checkpoint in the case for some deeper or broader story. In some speculative corners, theories have been advanced where universes with slightly different values for dark energy, dark matter, or fundamental particle physics could coexist, split off, or even bump up against each other, at least for a cosmic instant. Scientists are careful. They always double and triple check whether the oddities Hubble records could just be artifacts of how we look, limits of sensitivity, or the result of hidden biases in the way data is filtered and analysed. Cosmic background surveys, for example, need to account for all the noise added by faint foreground galaxies, dust, and even our own Milky Way's structure. Time and again, though, some patches, like the cold spot, survive all this cleaning, looking just as strange in every new round of study. New telescopes, like the James Webb Space Telescope, continue to re-examine areas flagged by Hubble. There's a hope that different wavelengths, precision, and scanning methods might reveal complementary information. If the signals get stronger or more persistent with each generation of instruments, that will tip the scales further, either crowding out the multiverse hypothesis or making it harder and harder to ignore. The possibility of a multiverse also opens up other lines of scientific thinking. For example, if other universes have different amounts of dark energy, then only some would be suitable for galaxies and life to form. Some theorists argue that the fact ours appears so just right might be a cosmic selection effect. We find ourselves here precisely because our universe happens to have the right mix needed for stability. It's a subtle argument, but one that gains more scientific traction as each fresh dataset shows us peculiarities that aren't easily explained with just the physics we know. Another hook comes from quantum mechanics. Some versions of quantum theory, especially ones tied to the many worlds interpretation, predict that every possible way that events could happen does happen, each in its own universe. These are more philosophical than directly observable, but Hubble's maps and surveys provide a way of testing if at least some aspects of this overlapping of realities make measurable marks in our cosmic neighborhood. Culturally, the thought that Hubble's precise, hard-won data could be pointing to alternate universes has fired the imaginations of scientists and the public alike. There are documentaries, debates, and academic battles about whether the cold spot or the odd alignments are smoking guns for the multiverse or just especially weird pieces of cosmic luck. For a lot of working astronomers, though, the main fascination is all about chasing the unexplained as far as evidence and reason will allow. So far, the observable universe is just that, observable, and that's where all hard conclusions are drawn. Still, with every deep field image, every mapped cold spot, every small but persistent anomaly, Hubble's cameras keep nudging the boundary of what scientists feel they can claim to understand. The telescope has become a kind of indirect explorer, mapping the faint traces of what could be a much, much larger landscape than anyone imagined just a few decades ago. This ongoing search pushes astronomers to invent smarter ways of distinguishing between normal cosmic randomness and true outliers. Each new simulation run is compared against the real sky, painstaking statistical battles played out over years. Even as most of the strange findings eventually get explained in ordinary terms, some stubbornly resist, staying just on the edge of what science can clearly describe. None of this guarantees that the multiverse is real, only that the boundaries of knowledge are being redrawn with each pass. Hubble's role is unglamorous, but crucial. Its images don't show universes stacked on one another, but they do systematically map out the few spots, patterns, and structures that challenge the one universe story. The better scientists understand the plain facts of our cosmos, the more the fragments that don't fit take on meaning as possible signs of a wider, wilder reality beyond our cosmic horizon. So, So the more that Hubble's work displays the unexpected, a cold spot here, a cosmic wall there, a strange alignment in the most ancient light, the more cosmologists have to expand their thinking or admit that the universe might be only one piece of an even grander puzzle. Each year, as the data piles up and the models get more refined, the cosmic story gets richer, more surprising, and the hunt to explain the strange gets just a little sharper, all because Hubble keeps looking deeper than anyone thought possible. With all of these hints about a universe that could be far stranger than anyone imagined, maybe even part of a much broader multiverse, the job of Hubble and telescopes like it takes on a different level of seriousness. At its core, Hubble's role has always been to keep pushing the limits, showing scientists both new mysteries and sometimes hard, uncomfortable truths. One of the biggest and most practical puzzles that Hubble has helped to tackle is this: what is the ultimate fate of our universe? That question, which maybe sounds more like philosophy than science, is actually deeply rooted in the measurements Hubble keeps sending back. Every deep field, every scan of a distant supernova, every detailed map of swirling galaxies, each one brings more data to help answer a mystery that has fascinated people for generations. When you break down what it means to ask how the universe will end, you're talking about some of the most basic physics at the largest possible scales. Hubble's work is crucial for several reasons. First, it provides the clearest and farthest look at galaxies, which lets scientists measure how quickly the universe is expanding at different points in time. By looking at how galaxies are moving away from us now and how that motion has changed across billions of years, astronomers have been able to come up with various predictions for what the future holds. When Hubble observes distant supernovae, the explosions of massive stars that work as standard candles for distance, these blasts allow us to chart out exactly how fast space is stretching, not just here and now, but throughout cosmic history. The earliest models for the fate of the universe focused just on regular matter, gravity, and the expansion that astronomers first discovered in the early 20th century. Based on simple logic, if there was enough mass in the cosmos, then all that gravity could eventually halt the expansion. From there, two big scenarios played out. In one, called the Big Crunch, the universe would slow down, stop expanding, and eventually reverse, pulling everything back into a hot, dense blob, like rewinding the Big Bang in slow motion. In the other option, if there wasn't enough mass, the universe would keep growing forever, but at a slower and slower rate, cooling and thinning as galaxies drifted farther apart in an endless big freeze. But here's the thing, Hubble's data didn't fit either story very well. By the late 1990s, Hubble's ability to spot distant supernovae, paired with other big surveys, led to the surprise discovery that the universe's expansion isn't slowing down at all. Instead, it's speeding up. This meant that not only would the universe keep expanding, but it would do so faster and faster as time goes on. The cause of this acceleration is what researchers now call dark energy, a kind of repulsive force or energy baked into the fabric of space itself. Hubble's results showed this acceleration is real, not a fluke. That single discovery eliminated the classical Big Crunch scenario, and it means our long-term outlook is much more extreme. With Hubble's data in hand, astronomers now have to weigh different kinds of endings that are all linked to the unknown properties of dark energy. The evidence so far points toward a few main possibilities that you hear scientists discuss. The one that most models lean towards is a version of the Big Freeze, also called heat death. In this model, as the universe expands at an ever-increasing rate, galaxies get farther apart, stars use up their fuel, and eventually even the atoms in those stars are left isolated in the cold. Over immense spans of time, everything spreads so thinly that energy exchanges grind to a halt, and the universe just cools into darkness. There's a more dramatic and unsettling version called the Big Rip, which becomes possible if dark energy's behavior changes over time and grows stronger. In this scenario, the repulsive force that's driving expansion doesn't stay constant, but starts pushing harder and harder. That would eventually mean not just the galaxies, but even clusters, solar systems, and down the line, individual planets and atoms are ripped apart as the very fabric of space stretches over and over at a runaway pace. Nothing, not even gravity or atomic forces, would be able to hold things together in the universe's last moments. Then there's a third option, the so-called cosmic rebound, or bounce. While this is a minority view given Hubble's observations, some theorists suggest that if something unexpected happens, maybe a sudden shift in dark energy or an interaction with something truly unknown, the universe could slow down and rebound back together, either ending in a new Big Bang or settling into a different kind of steady state. Most current evidence from Hubble and the other big cosmology missions, though, doesn't support this idea. What is unique about Hubble's role is that it provides the numbers and time-stamped snapshots needed to compare all these options side by side. The telescope's measurements of the rate of expansion, the distribution of distant galaxies, and the history of star formation all feed into huge computer models that simulate the future. Every new, deeper image or detailed time series helps eliminate more possibilities and pin down which scenario is more likely. Hubble has made it possible to construct cosmic timelines, not just for individual galaxies, but for the entire structure of the universe, by looking at real objects from every major period in its history. Another big contribution from Hubble is helping answer what will happen to galaxies themselves, especially the ones most like our own. The telescope's surveys have shown that galaxies aren't just drifting away. They're evolving in complex ways, colliding, merging, and sometimes cannibalizing smaller neighbors. These slow-motion fireworks witnessed across billions of years have broader meaning when you ask about the long-term future. Based on the rate of mergers, dark matter measurements, and the structure of clusters, astronomers use Hubble's archives to predict what local galaxies will look like hundreds of billions to trillions of years from now, even long after stars have burned out. There's another twist that Hubble helped clarify. The cosmic background light it records tells us there's a hard limit to how much of the universe will remain visible in the deep future. As expansion speeds up, more and more galaxies will cross what scientists call the cosmic event horizon. That means their light simply won't be able to catch up to us. Those galaxies will disappear forever from any telescope's view, no matter how powerful. Fast forward far enough, and observers on Earth or anywhere would one day be able to see only a handful of galaxies, eventually perhaps only the Milky Way's own cluster. The universe, beyond some point, turns truly dark and isolated on cosmic scales. Hubble's ability to measure the chemical evolution of galaxies, looking at their metallicity, or the amount of elements heavier than hydrogen and helium, feeds into the bigger picture of star formation's future. Data shows that galaxies keep using up their raw material for building new stars, and as the supply runs down, star birth slows. In a far future where new stars are rare, starlight fades, and what's left are long-lived red dwarfs, black dwarfs, white dwarfs, neutron stars, and black holes. Hubble's deep surveys of old star clusters and faint, distant galaxies give astronomers benchmarks for how quickly these changes occur. On a more human scale, there's the question of what happens to planetary systems, the building blocks of life as we know it. Hubble hasn't been used primarily as a planet hunter, but its fine imaging has contributed to understanding how planets and dust clouds evolve in the aftermath of supernovae and when stars die. The long-range models, based in part on these observations, predict a time when all stars finally burn out, leaving behind corpses scattered through a universe growing ever colder and more empty. There's also a direct impact from all of this knowledge on physics research here on Earth. The measurements that track the universe's growth, pushed forward by Hubble's steady improvements in accuracy, are ongoing tests for the best ideas in physics, from general relativity to quantum field theory. Any mismatch, strange slowdown, or curve in the numbers sends theorists back to the drawing board, looking for something that could change the assumed future. So far, though, the trend is remarkably stable. As far as anyone can tell, the universe is heading for a cold, endlessly expanding fate. But Hubble's pictures do more than just show what will happen. They highlight how little we know about the drivers behind this ending. Dark energy, the main cause of the accelerated expansion, remains almost totally mysterious. While its effects can be mapped and measured, even after decades of Hubble data, scientists do not know what it is made of, where it comes from, or whether it might change over truly huge stretches of time. As long as those questions remain, every confident prediction comes with a long list of uncertainties. Telescopes following in Hubble's footsteps, like the James Webb Space Telescope, are meant to fill in those gaps, but for now, Hubble is the benchmark. What keeps astronomers and physicists motivated is that hidden in Hubble's archive could be patterns or rare outliers that upturn what's expected. The tiniest difference in how distant galaxies behave, a small unexpected fluctuation in the cosmic background, or an anomaly in the rate of supernovae, can ripple up into changed predictions about the end. There's an ongoing race to refine every number, a cleaner Hubble constant, a better measure of how much dark energy there is, or a more precise map of dark matter's effects, because each number could tip the scales. One more thing Hubble has shown quite clearly. The universe doesn't care about human ideas of importance or centrality. When you look at deep fields full of thousands of galaxies, most of which never even interact with our Milky Way, it drives home just how immense and neutral the universe is. The Earth and its solar system are just tiny visitors in a cosmic story that will unfold whether we're there to watch or not. As the expansion accelerates, the place of life and planets in the overall timeline shrinks. Most of the universe's future will be long after Earth and its descendants are cold and dark. Still, the push to understand all of this has its own kind of momentum. Even as Hubble catalogues what appear to be the signs of a universe fated for emptiness and cold, the data inspires new searches for gaps, loopholes, or unlikely escapes. Until dark energy is fully understood, some hope remains that the diagnosis for cosmic destiny could shift. The identity of this mysterious force is the single biggest factor in the models, so researchers keep combing the archives for anything. A supernova out of place, a galaxy behaving unpredictably, an unexpected pattern in old light that might offer clues. If there's a central image that summarizes Hubble's role, it's those iconic ultra-deep fields, staring into what looks like nothing and finding thousands of galaxies at every possible stage of their existence conveys the scale and scope of what's on the table. These images let astronomers count, measure, and, for the first time, make realistic projections that stretch trillions of years into the future. Each new generation of deep sky images refines the outcome, makes better predictions, or rules out something once thought possible. The best conclusion, at least so far, is that the universe's fate looks cold, dark, and everlasting by all available data. Barring the most unexpected surprise in physics, galaxies will keep receding, stars will dim, and everything will get colder as energy becomes more and more dilute. The Hubble Space Telescope didn't just help predict this, it built the whole modern argument. By delivering clean views of distant objects, by serving up the data for dozens of teams around the planet, and by providing the yardstick used for the deepest questions, Hubble did more than any other single mission to turn ideas about the universe's destiny from speculation into science. Yet even as it does this, the telescope's work is far from over. Every new discovery about the structure, composition, and motion of the universe could bring a twist in the story. The next unexpected measurement, maybe from Hubble or one of its successors, could challenge the fate predicted by today's models. Until then, the search and analysis goes on, with one eye always on the endpoint and the other on the ever deeper, ever stranger cosmic landscape Hubble has revealed.